Hello colleagues. Welcome to our final lesson on machine learning methods, reinforcement learning. In this lesson, we will explore what reinforcement learning is, how it works, and why it demands a special approach to governance. We will become acquainted with its key components, algorithms, metrics, risks, and real-world examples. Most importantly, we will understand how to make such systems safe and reliable. And, of course, as is our tradition, at the end there will be a bonus quiz to test your knowledge. So please subscribe, if you haven't already, to our channel so you won't miss any upcoming lessons. Reinforcement learning is a machine learning method in which an agent, following its policy, takes actions in an environment, receives rewards for those actions, and, by evaluating changes in the environment state, learns to choose actions that maximize cumulative reward. Let's examine this definition in greater detail. Agent, our self-learning AI program. Environment, everything external to the agent, it accepts the agent's actions and changes its state according to predetermined rules. State, the current data or situation in the environment as seen by the agent, for example, the positions of the pieces on a chessboard. Action, the specific move the agent makes in that environment, a chess move, buying or selling a stock, etc. Reward, a numerical, good-bad, signal for each action, which tells the agent how close it is to its goal. Policy, the agent's internal strategy or set of rules by which it decides which action to choose in each state so as to earn the greatest future rewards. Imagine your child learning to play a video game without ever reading the rules. The child is our agent. They look at the game screen, that is the environment state. They see where their character stands, where enemies lie in wait, where power-ups appear. Based on that, they decide what to do next, move right, jump, shoot. That is the action. Once they perform the action, two things happen: the game renders a new scene, our new state, showing the character's movement and enemies' reactions. And the game tells them whether they did well by awarding points for collecting a bonus or subtracting a life for colliding with an enemy. That is the reward. The child isn't learning from a textbook of rules, but by trial and error. Over time, they discern which actions in which situations yield good outcomes, which yield bad ones, and develop their own playing policy. Eventually, they complete the game. Reinforcement learning is not simply a sequence of steps but a well-organized cycle of decision-making and improvement. First, the agent assesses the current state of the environment, its starting point. Next, following its policy, it decides on the most sensible action for that situation. It executes the chosen action, directly affecting the environment. In response, it receives a reward, either a positive reinforcement or a penalty. This is feedback. The agent then observes the environment's new state and compares it to the original. Finally comes the pivotal moment, the policy update. The agent adjusts its strategy so that next time it will act more intelligently and accumulate more reward. And then the cycle begins anew. Step by step, through interaction and analysis, the agent becomes ever more effective. This is the essence of reinforcement learning. But there is a significant complexity: good results may not appear immediately. To defeat the final boss, one must first collect weapons and level up the character. In other words, some actions may seem disadvantageous now but yield greater reward later. The approach founded on the Markov decision process with its 5 key components is fundamental to reinforcement learning theory. Let us briefly review each of these pillars. States. All the information the agent can perceive about its current situation. In chess, this is the arrangement of all pieces on the board. In an autonomous vehicle, it might be camera and radar feeds, GPS data, speed, and road conditions. Critically, the agent can only make decisions based on what is included in its state description. Omit vital information, and the agent will act without awareness of those aspects. Actions. The complete set of decisions available to the agent. In chess, this means every legal move; in an algorithmic trading system, actions like buy or sell. Critically, we must carefully constrain the action set to exclude potentially harmful or dangerous choices. A vehicle control system, for example, should never be able to accelerate 10 times the legal limit, even if technically feasible. Transition probabilities. Describes how the environment reacts to the agent's actions. For instance, when I flip a light switch, the light usually turns on, but there is a small chance the bulb has burned out or the power has failed. Transition probabilities capture this uncertainty. In real-world tasks, we often do not know these probabilities in advance, the agent must learn them through experience. Reward function. The most critical, and potentially hazardous, element from a governance perspective. The reward function tells the agent what is good and what is bad, it is the AI's system of values. Misdesign the reward, and you may end up with behavior that is formally optimal but practically useless or even harmful. For example, an office cleaning robot rewarded merely for the amount of trash collected might scatter garbage before picking it up, maximizing its reward while defeating the true purpose of cleaning. Gamma, discount factor. A parameter that determines how far-sighted the agent is. A value near 1 means the agent values today's reward almost as highly as that of a year from now. A value near 0 implies focus solely on immediate gains. Imagine teaching a child savings. With a high discount factor, the child will patiently save for a bicycle for months. With a low one, they will spend all their money on candy immediately. Documenting and justifying this choice is critical, as it dictates whether the AI will plan for long-term consequences or pursue short-term gain. The Markov assumption claims that the future depends only on the present, not on the past. It is akin to saying that for deciding your next chess move, you need only see the present board state, not how you arrive there. In real life, this rarely holds. If a patient complains of chest pain, a doctor needs not only the current symptoms but also medical history, lifestyle factors, and genetics. Accordingly, modern reinforcement learning theory includes alternative and extended approaches that relax the classical MDP's limitations and adapt to more complex tasks. However, their study lies beyond this course's scope. When we do not know precisely how the world operates or what constitutes a good outcome, we cannot immediately deploy an agent into the real environment. Imagine teaching a child to drive by placing them behind the wheel on a highway. A sandbox is a simulation where the agent can safely make mistakes. For autonomous cars, this means driving simulators; for financial systems, historical market data; for medical systems, anonymized clinical records. It is crucial that the sandbox be as realistic as possible. If the simulation is oversimplified, the agent may learn strategies that work there but fail in reality. Each of these 5 components demands thorough documentation and justification. States. Record exactly what information is provided to the agent and what is excluded. Document data sources, selection criteria, and potential biases. This foundation supports assessments of fairness and privacy. Actions. Clearly describe the allowable actions and any constraints. Record the decision process for permitting or prohibiting each action. This is central to ensuring system safety and ethical behavior. Transition probabilities. Describe the methods used to model the environment and the data sources for estimating probabilities. Document assumptions, model limitations, and validation procedures. This underpins evaluations of system accuracy and representativeness. Reward function. Provide a detailed rationale for chosen metrics and weightings. Document stakeholder consultations and any anticipated side effects. This captures the system's values and objectives. Discount factor. Justify the planning horizon and its social implications. Record how it influences short and long-term outcomes. This reflects broader policy and responsibility considerations. Such documentation creates the basis for auditability, reproducibility, and system improvement. Imagine you wish to teach 4 different individuals to drive. Each has a unique learning style, just as the 4 main families of reinforcement learning algorithms solve the same problem in fundamentally different ways. Value-based algorithms. These operate like a savvy investor who knows the exact return of every stock in a portfolio. For each possible investment in each market situation, they compute the expected long-term profit and choose the best. Picture trading on the stock exchange, where for every trade the investor calculates, buying this share now will yield 5% per month on average. The algorithm builds a table mapping each state, market condition, and action, buy or sell, to its expected return. Policy-based algorithms. These teach the system directly what to do in each situation, without first computing a value estimate. They resemble an experienced driver who feels the road and makes decisions intuitively, like a musician playing from sheet music by instinct or a veteran physician diagnosing by gut feeling. The algorithm forms a direct mapping from state to action. Actor-critic algorithms. A hybrid approach combining policy-based and value-based ideas. In practice, the actor says, "I will turn left." The critic replies, "Good choice, that will yield +5 points," or, "Bad choice, you'll lose 3 points." The actor learns from the critic's feedback, and the critic learns to better evaluate the actor's actions. Model-based algorithms. These first build an internal model of the world, then use it for planning, much like a skilled chef who knows how each ingredient behaves under heat and time. The algorithm observes the environment, constructs a model. For example, if I raise the price by 10%, sales drop 5% but profit rises 3%, and then plan sequences of actions. What if I discount first, then raise price, then launch an ad campaign? Unlike familiar classification metrics such as accuracy, precision, recall, or F1 score, which measure prediction accuracy against labeled data, reinforcement learning demands different metrics. Cumulative return. The primary success metric, defined as the sum of all rewards an agent receives over an episode or series of steps, discounted so that earlier rewards count more than later ones, akin to money's time value. For example, an autonomous car might earn 10 points for each second of safe driving, 100 points for a successful park, and lose 1,000 points for a crash. The cumulative return captures overall trip utility. Reward hacking. When an agent exploits flaws or ambiguities in the reward function to maximize reward in unintended ways. A classic case, a cleaning robot rewarded per piece of trash collected might first scatter trash around before picking it up, maximizing its reward while defeating the cleaning objective. Sample efficiency. How effectively an algorithm uses available data to learn. High efficiency means achieving good performance with fewer data or interactions. Imagine two driving students, one masters driving in 10 lessons, the other in 100. The first has higher sample efficiency. Regret. The difference between the reward the agent actually received and the maximum possible reward had it chosen optimal actions. A trading algorithm might earn $800,000 when perfect decisions could have yielded $1 million, resulting in $200,000 of regret. Safety metrics are a means of measuring how safely and ethically an artificial intelligence behaves during training and operation. The main types of these metrics are rule and constraint violations. This occurs when the AI crosses a boundary and does something that is forbidden. Discrimination and unfairness. We check whether the AI treats different people differently based on their gender, race, or age. Systemic risks. We track how often the system fails and what harm such failures may cause. European requirements for high-risk AI systems demand detailed reporting specifically on safety metrics. Companies must be able to document not only the successes but also the risks of their systems. We will study all the nuances of this in future lessons. For now, notice how a very simplified summary of an AI model's results might appear. We will conduct a more detailed analysis of documenting such systems in practical lessons. At this point, you should once again recall that documentation is not merely a theoretical principle of AI governance but also a legal requirement. Let's examine the primary risks in reinforcement learning. Misaligned rewards occurs when the AI does not achieve your true objective but instead exploits a flawed reward definition. For example, if you measure your cleaning robot only by speed, it might clean by shoving trash under the sofa, technically fast, but not actually cleaning. Unsafe exploration. During training, the AI may attempt dangerous actions. Like a child testing what happens if they stick a finger into an electrical outlet, or a drone flying through a crowd simply out of curiosity. Simulation to reality gap. an agent that performs flawlessly in simulation can fail catastrophically in the real world. A self-driving car that corners perfectly in a virtual environment may crash on actual roads because it didn't learn to handle rain, potholes, or unpredictable drivers. Lack of explainability. Modern AI models often have millions of parameters, making their decisions effectively black boxes. This opacity prevents users from understanding why a decision was made and undermines their right to a clear explanation. Goal misalignment. The AI optimizes for the specified reward rather than for socially beneficial outcomes. For instance, a taxi routing system might choose shortcuts through narrow alleys or pedestrian zones to minimize travel time, speeding up trips at the expense of safety and legality. Let's review the governance controls we implement at each phase of system deployment. Development. A cross-functional committee, comprising stakeholders from engineering, legal, compliance, and business, reviews and validates the AI's objectives to ensure they are correctly specified and aligned with organizational goals. Training. The agent learns in a secure, simulated environment with strict limits on permitted actions. Emergency stop mechanisms and action filters prevent the AI from taking harmful or out-of-scope steps during its exploration. Validation. Offline testing is conducted without real-world interaction. This includes adversarial scenario tests, fairness audits to detect potential bias against protected groups, and robustness evaluations under edge case conditions. Deployment. Prior to going live, a kill switch is put in place, an immediate shutdown control monitored by a dedicated operator who can intervene if the AI misbehaves. Post-launch monitoring. Continuous oversight tracks performance drift, safety incidents, and compliance metrics. Regular reassessments and incident response drills ensure the system remains on course. All of these steps are meticulously documented to meet international standards, and the organization must maintain a formal incident response plan outlining exact procedures for any unexpected outcome. Regulators routinely audit the existence and quality of these plans as part of their high-risk AI compliance requirements. Real-world case studies. OpenAI 5 played Dota 2, an extremely complex game with live opponents and uncertainty, entirely in simulation. Millions of matches between self-play copies yielded a robust AI whose strategies even professional teams found surprising. This demonstrates the power of RL in fully controlled digital worlds. YouTube recommendations maximize watch time but may promote increasingly extreme content, contributing to radicalization and polarization. In Europe, such systems are classified as requiring special oversight. Warehouse robots at Amazon use RL for aisle navigation. In physical environments, robot-human collisions are possible, so these systems fall under high-risk categories in the EU AI Act and must meet strict robotics safety standards. Adaptive cruise control systems learn offline from data and then undergo rigorous scenario-based testing in accordance with automotive safety regulations. The closer an RL system interacts with people and the physical world, the stricter its safety and governance requirements. And now, friends, let's see how well you've absorbed the material from this lesson. What is an agent in reinforcement learning? Which of the 5 key components of an MDP is the most critical and dangerous from a control perspective? What does a discount factor gamma close to 0 mean? What is reward hacking? Which class of reinforcement learning method simultaneously employs a policy model and a value estimator? What is the sim-to-real gap? Pause the video and write your answers in the comments, or let us know what you found challenging and we'll discuss it together. If you enjoyed the video, please give it a thumbs up and subscribe so you don't miss the next lesson. Reinforcement learning is a powerful tool that can automate complex tasks but demands exceptional caution. It opens possibilities for autonomous systems, robots, drones, recommendation engines, yet risks stemming from misdefined objectives can lead to unpredictable consequences. Safety is ensured through careful reward design, sandbox training, gradual rollout, and continuous monitoring. Risk management, transparent documentation, and early collaboration with safety experts enable reinforcement learning to be both beneficial and secure.